All right, today we're diving into a discovery that completely flips our sense of reality on its head. I mean, it proves the universe is way, way stranger than it looks. So, let's get right into it.
And look, this isn't just any discovery. We're talking about work so groundbreaking it snagged the Nobel Prize in Physics. And it was all for an experiment that took these bizarre, spooky rules from the quantum world and proved they don't just happen with tiny, single atoms. Oh no, they showed it can happen with huge systems. We're talking objects with billions of particles all acting together as one.
So, let me just ask you a simple question. Can you walk through a solid wall? I mean, of course not, right? If you throw a ball at a wall, it's going to bounce back. Every single time. That's just basic common sense. We'll get ready because common sense is about to go right out the window. Because, you see, down in the quantum realm, the world of tiny things like electrons and photons, the rulebook is totally different. It gets really, really weird. Imagine you shrink that wall down to a microscopic size and fire a single electron at it. Now, there is a small but very, very real chance that the electron won't bounce back. Instead, it will just pop into existence on the other side. And that is the kind of weirdness we are going to unpack today.
All right, so this phenomenon, this impossible leap through a solid barrier, it actually has a name. It's called quantum tunneling. And that right there, that's the core idea that won these physicists the Nobel Prize.
So what is it, really? Well, quantum tunneling is when a particle does something that our everyday physics says is absolutely forbidden. It passes through a barrier, like a wall, without ever actually breaking it or even being inside it. It's on one side, and then suddenly, poof, it's on the other. It really is like the universe is pulling off its greatest magic trick. And the magicians who actually pulled back the curtain on this whole thing? Well, they were John Clark, Michael Debye, and John Martinez. We're going back to the 1980s at the University of California, Berkeley. That's where they put together this incredible experiment to see just how far this quantum weirdness could actually be pushed. Okay, to really get how they pulled this off, you have to do something first. You've got to completely stop thinking about particles as tiny little billiard balls. Seriously, that's the image that messes with our intuition. The quantum world, it demands a totally different way of looking at things.
And this comparison really gets to the heart of it, right? In our everyday world, things are solid. They're like little billiard balls. They have an exact location, and when they hit something, they bounce off. Simple. But in the quantum reality, objects are way more like waves. They're kind of spread out in space, with fuzzy, indefinite edges. You can't talk about certainties, only probabilities. And because of that waviness, they don't just bounce. Part of that wave can actually kind of seep right through a barrier.
That's exactly it. A quantum particle isn't just in one single spot. It exists as this wave of possibilities. Scientists call it a wave function. And where the wave is tallest, that's where you're most likely to find the particle. But, and this is the absolute key, the edges of that wave, they just kind of fade out, but they never actually hit zero. And that means there's always this teeny tiny, but not zero, chance that it could show up somewhere completely unexpected, like, you guessed it, on the other side of that wall. Now, for most of the 20th century, scientists figured this kind of strangeness was locked away in the subatomic world. You know, it was a rule that applied to a single electron here, a single atom there, but not for anything bigger. I mean, you never see a baseball just tunnel through a fence, right? So the big nagging question was, where's the dividing line? Is there a point where the quantum rules just stop and our normal classical rules take over? So that's exactly the question the team at Berkeley set out to answer. They built this incredibly clever device to test if a large group of particles, what you could call a macroscopic object, could make this quantum leap all at the same time. And the special tool they built to do it, it's called a Josephson junction. First things first, to build one of these, you need a special ingredient, a superconductor. Now, what's that? Well, if you take certain materials and cool them down to temperatures even colder than deep space, something mind-blowing happens. Electricity just flows through them with zero, and I mean zero, resistance. It's like having a current that could loop around the planet forever and never lose a drop of energy. This perfect flow, it's a purely quantum thing. Okay, get this. Inside that superconductor, the electrons, which normally hate each other and push each other away, actually start pairing up. They form these things called Cooper pairs. And then billions of these pairs all start moving together in perfect lockstep, like this giant synchronized army. The whole group behaves like one single massive quantum entity, with one single wave function describing all of them. And that was the big macroscopic object they wanted to test. So how do you actually test something like that?
Well, you build a Josephson junction. Here's how it works. You take two of these superconductors and you put a super thin insulating barrier right between them. It's like a sandwich. Now, for any normal electric current, that barrier is a total dead end, an impenetrable wall. The electrons should just slam to a halt. But for a quantum system? Well, that's what the whole experiment was about.
And I mean, the setup for this experiment was just a masterpiece of precision. First, they built their junction. Then they used this special high-tech refrigerator to cool it down to just a tiny fraction of a degree above absolute zero, colder than anywhere in the natural universe. They had to shield it from any possible interference, and then, very carefully, they started to pass a current through it, watching their instruments like hawks for any tiny change in voltage.
And this was their really audacious goal. This wasn't about just a few single electrons hopping across. No way. They wanted to see if the entire collective wave function, the quantum state for all those billions of Cooper pairs, could tunnel through that barrier all at once, as a single object. The real question was, could a big macroscopic system actually do the quantum leap?
So, the stage was set. They ran the experiment, they slowly ramped up the current, their eyes glued to the instruments, just waiting to see what would happen. And what they found, well, it was the exact proof they'd been hoping for. At first, everything was going just like you'd expect. A supercurrent was flowing with zero voltage, just like it should. But then, as they pushed the current up to a specific critical point, something totally unexpected happened. A voltage spike, just poof, appeared out of nowhere. Now, why is that a big deal? Because that voltage spike was the signal. It was the little burst of energy released as the entire quantum system escaped and tunneled clean across that barrier, all as one. But, great scientists have to be great skeptics too. They had to ask themselves, how can we be absolutely sure this is quantum tunneling? Couldn't it be something simpler? For example, maybe a little bit of leftover heat energy was just rattling the system around, jiggling it hard enough to eventually kick it over the barrier. That's a normal, classical thing called thermal activation.
And this right here is the smoking gun. This is how they proved it. See, if the system was being kicked over by heat, the escape rate would depend massively on temperature. A little more heat, a lot more escapes. A little less heat, way fewer escapes. But what the team saw was just incredible. As they cooled their experiment down to the absolute coldest temperatures possible, the escape rate just flattened out. It stopped changing. It became totally independent of temperature. And that could only mean one thing. The system was going through the barrier, not over it. It was, without a doubt, quantum tunneling.
Now, this discovery wasn't just some neat little academic curiosity. Oh no. Proving that big, macroscopic objects actually followed these weird quantum rules had huge, profound implications. In fact, it laid the groundwork for technologies that are literally changing our world as we speak.
I mean, just think about the story here. Back in 1935, you have Schrödinger coming up with his famous cat-in-a-box idea, basically to show how absurd and ridiculous quantum theory sounds when you try to apply it to big things. Then, fast forward to the 80s, and these guys come along and prove that the absurd is actually how the universe works. And now, today, the exact same principles from those early experiments are being used to build the superconducting qubits that power the most advanced quantum computers on the planet.
And what I personally love most about this story is the why, the motivation behind it all. I mean, this monumental discovery wasn't driven by some grand plan to build a quantum computer. They had no idea that would happen. It was driven purely by curiosity, by that fundamental human need to just know, to test our ideas and figure out how the universe really works.
So in the end, what this work really proved is that those weird, fuzzy, probabilistic rules of the quantum world, they aren't just for the tiny stuff. They are the fundamental rules for, well, for everything. This experiment showed us that our reality is so much stranger and, frankly, more wonderful than our common sense could ever suggest. And it just leaves you with this thrilling question: if just following our curiosity led us to this discovery, what on earth will it uncover next?